Yeah.
So, ladies and gentlemen, I think that I don't need to explain the importance of research in extremes and extreme event to this audience. Also, research in causality, I mean, this research in causal discovery using time series is very intensive in present time, but it is surprisingly low number of studies which try to connect the two topics. So in order to start from a broad perspective, we study complex systems which consist of many elements, and in order to understand the complex behavior, we need to understand the interactions. So how to detect and describe these interactions? It is based on time series analysis when we record time evolutions of subsystems of our complex systems, and then we try to translate different kinds of interactions into the language of time series analysis. So if we want to find any kind of interactions or coupling, we look for dependence. If we would like to find more specific cooperative behavior like synchronization, we are looking for some kind of functional relations in a reconstructed phase space. And talking about causality, we search for predictability. So if we have two random variables, say x and y, with some probability distribution function px and py, we know that these two variables are independent if the joint distribution is equal to the product of px times py. So if we take this ratio of the joint and the product of marginal distributions, for independent variables, it is equal to 1, and logarithm of this is equal to 0. If there is some dependence, this is different from 0. So if we take this expression and make average over our probability space, we will get some measure of digression from independence, and this measure is known in information theory as mutual information. It is interpreted as the amount of common information in two variables, but it also has some nice properties, like it is 0 for only if the variables are independent, and any kind of statistical dependence, which can be more general than just correlations, then this measure is positive. And it can be written in the form of entropies. We will also use something which is called conditional mutual information, and this is a measure which measures dependence between two variables given the third variables. It's something like Dim mentioned with partial correlation, that if you would like to find a relation between two variables and remove the possible influence of the third, that we will use this conditional mutual information, which can be also expressed in entropies. And of course, if x and y are independent of z, then this equation holds. So conditional mutual information between x and y measures some kind of net dependence or net common information between x and y without possible influence of z. So now we are going to the question of causality. This idea, which comes in from the father of cybernetics, Norbert Wiener, and was formalized by Sir Granger, is also now called Granger causality, is based on the idea that if one variable, say x, is causal to y, then knowledge of present state of x would improve the predictability of y in comparison with predictor which is based only on the history of y. This causality was formulated using linear autoregressive processes, and it was successfully applied in many areas, and also it has many generalizations into nonlinear system. One of them is just application of the conditional mutual information, in which we use this kind of formulation of information-theoretic function that we measure dependence between y in presence t and state of X in future, T plus tau, and this is taken conditionally on the presence and some steps into history of X. So this conditioning means that we are removing some possible information about common history, and we really measure just influence of Y now to the future of X. So we can interpret this conditional information, which is also known as transfer entropy in the literature, in the term of Granger causality as the cause or predictor, and the effect or the future, and there is the conditioning. As I said, the conditional or the mutual information is the general measure of dependence, but when it can be expressed for Gaussian systems, and then it is equivalent to Granger causality. This is why that causality is many times interpreted as information transfer from the cause to the effect. And now, typically we work with Shannon entropy. I showed you how mutual information can be expressed in terms of entropies, and so this is the well-known definition of the Shannon entropy. But for systems which have non-normal, or especially if the systems which have distributions with heavy tails, some different entropy concepts were proposed. We will use so-called Rényi entropy. So this is the definition of Rényi entropy, in which the probability distribution functions is in the power of alpha, and this alpha is a Rényi parameter. And it is interesting that for it converges to Shannon entropy for alpha approaching to 1. Otherwise, it has some interesting properties. So we can go from the Shannon information to Rényi information and ask what we will see if we have some data with distribution which are not typically normal. I will show you one numerical example. So we define variable C as a cause as just simple AR1 process, when the CT is a function of its previous state and the noise, and the other variable X will be just a Gaussian noise. And now we define the effect variable ET. So this is again AR1 process, but it is defined using its history, but also C. So this is the typical example of C Granger causes E. But in addition to this AR process, we put some influence from X. So anytime when the X crosses 3 or -3, then the next value of E is set to 1.8 or -1.8. So we will use this data as our examples. So here we have pieces of data. So this is variable C, this array process. X is just Gaussian white noise. And here is ET, which is influenced by C. And here you can see some events caused by variable XT. So if we look at the histogram or estimation of probability distribution function of variable E, then it is practically normal distribution just here on the very tail. So here we have zoomed this picture. We have seen some heavy tail because of those extreme events which are induced by variable X. So now if we take this probability distribution in the power of 3, we can see that exponent which is larger than 1 attenuate or make stronger the probability distribution around the mean, while if we take power to 0.3, then the tails are amplified. So we can ask if this taking power of a probability distribution can amplify particular part of distribution. Can the reformulation of the transfer entropy or conditional mutual information in the Rényi concept help to identify which cause if we can identify several causing variables, which of them is responsible for extreme events. So now we will look at the conditional information between C and E as a function of this Rényi entropy parameter alpha. And we can see this behavior in the direction from C to E. So this is the CMI quantifying influence of C to E. And this is the CMI in the opposite direction when there is no causality. And we can see that we have although the values are smaller, the behavior is practically the same. So if we look just to the estimates, we know nothing because there is some kind of behavior of the estimator. So what we need to do some statistical testing of these values. So this is the dependence of CMI alpha on alpha, and when we take one of the alpha equal to 0.9 here, and here we plot the dependence of CMI on the time like tau. So this forward time in the future. We can see here when the dark blue is the causal direction from C to E, that this causality lives only for some time, for some limited range of time lengths. So we will use this knowledge and in construction of so-called surrogate data. So in our statistical evaluation, we will use a tool of computational statistics, which is called surrogate data. When we are computing something, in our case, CMI from the pairs of data, and then we do some kind of randomization of our data sets. And there are many ways, but in this study, we use so-called circular shift of data. So we use this that we, I didn't tell that the principle of surrogate data is randomizing in the same way that we remove the property which we are tested for, while we keep all the properties. So as I shown you, because the causality lives only for a limited time, so if we shift the time series in large enough time shift, we can get numbers of null hypotheses of no causality. So we can do large amount of this kind of surrogateization. We compute empirical distribution, and we can ask how the volume which we got from our data differs from the distribution of this null hypothesis. So we can compute, for instance, z-score is data value minus surrogate mean divided by surrogate standard deviation. So we will get some kind of statistic in number of sigmas. So now, basically, when I repeat this data, so this is the variable E, and now the variable E shifted, circularly shifted, that this start is shifted here, and the end is put at the beginning. So this will be one realization of our surrogate data, and we will use this to evaluate statistical significance. So, and this is what I wanted to say, that here is the causality of the original data, and when we use summarization of surrogate data, we can see that everything is on the low, some kind of zero level. We always get positive values, but we will see that this will not be statistically significant. So now we compute again the dependence of CMI alpha on alpha, and this is in the direction from C to E, and blue line is from the data, and these green lines with whiskers is mean from surrogate data, and the range of plus minus two standard deviation. So here we can see that there is large area when this quantity is statistically significant, and now we can use the z-score. So this is the difference between the data and mean of surrogates in the number of standard deviation, where we can use a red line for in volume 2 as a level of significance R. And here we can see this light blue is the direction when there is no causality. So we can see that this is clearly under the significance line, while this blue one is in the causal direction, how C is influencing E. And what is interesting, this is highly significant for large alpha, and then for small alpha, it is going under the significance level. While when we look at the influence of X to E, so again, this is the results from the data and from the surrogates, and here we have Z-score. The orange is the Z-score in the non-causal direction, this is non-significant. And here, this variable which is causing extremes, we can see that it is not significant for large alpha, but is significant until the smallest alphas. So it seems that indeed, as we expected, about this influence of this parameter alpha, which is some kind of amplifier of effects on different part of probability distributions, that it seems in this very simple simulated example that it might work. And we can also look to the effect of these variables using conditional histograms. So when we plot distribution of variable E given C smaller than -1 sigma or -1 if it is normalized, we can see that this histogram is shifted to the left. So this is the blue one, while again the gray is a histogram from surrogate data, and here we can see Z-score, and so we can see that there is significant shift to the left, but the tails have probably the same probability. Here we can see this results for X. So here the effect is only on the tails. So now very quickly to real data, and we will use the temperature in two stations, winter from Frankfurt and spring from Dijon, and as possible causes, we will use North-Atlantic Oscillation Index, so-called blocking index, and Siberian high. So I think that most of you know what is it. And now the results for influence of NAO in Frankfurt in winter, we can see this kind of influence in which this is significant for large alpha, but falling down for small alpha. In blocking index, it is slightly left, but still it is not significant for small alpha. And what is interesting here, that we have some influence of Siberian high under the condition of non-positive NAO, which is mostly on the left side from 1. So when we look to the histogram, we can see shift for histogram for either NAO smaller than -1 in normalized index or blocking index larger than 0. In both cases, we can see shift of the histogram to the left, while for this Siberian high, we can see some increase on the tail, although so it is here. Even nicer result will be if we look to the spring data in Burgundy, in France. We can see that there is no effect of NAO in the spring. There is some effect of blocking, which is shortly before 1 and a little bit after 1, while this Siberian high, its significant effect spreads to very slow, small alphas. So we can compare when this significance disappears for blocking index, and here it disappears for Siberian high. And we can see in this conditional histogram that really this Siberian high, this condition of Siberian high larger than 1 sigma heavily increase the probability of the left tail. So that means of cold extremes in spring. So this is histogram using anomalies, and to see the real values, here we have daily mean temperatures, and here daily minimum temperatures. So we can see a heavy increase of probability of temperatures around -10. So this is something which happened this, and also last April, when there were spring frost, which were really disastrous for winemakers. Okay, so this, just to make a quick conclusion, we can see that NAO and block index in winter shifts the whole histogram, but of course shifting the histogram to the left means that some extremes are possible, while Siberian high, under the condition of non-positive NAO, has very specific effect on the left tails of the histogram, and this Rényi formulation of conditional mutual information really showed us that this effect is for small parameters of the Rényi entropy. So probably this concept can really help us to distinguish which of the causes, if we are able to identify several causes, then which one is specifically responsible for extreme values. Okay, so thank you for your attention.
Thank you very much, Milan, for the very nice talk. There is time for some questions. Maybe I start with a question. So you were showing this dependence on alpha of your new mutual information or causality quantifier. So that means if you have a large number of potential causes, you would scan all of them and identify which one has the peak for alpha smaller one in order to see what is the cause of the extremes.
Probably at this stage, I don't know with the recipe, but
so you think you could automize that in some sense, because here, of course, you have studied each individual curve.
So hopefully, so this is just a beginning in this direction. So maybe we will come with some automation later. So now it is really on this stage of manually computing and looping for the behavior.
So if I understand correctly, you now have a parameter to change and then detect the causality direction, right?
Yes.
This alpha. So if you, did you check, or is it possible that for some alpha, you have one direction, for the other alpha, another direction? So another of the challenges, going back to this talk, is that different methods give you different, sometimes contradictory information. And now within the same method, maybe depending on the parameters, you see one thing or the opposite.
I'm not sure if it's possible. Even I haven't seen, I have some colleagues who do these things in financial data, and they have seen something like that, but I'm not I was afraid that it was more some kind of artifacts. And so I'm not sure if it is possible, but you can find paper on financial data, and they have seen this.
Okay, are there further questions or into Zoom? Then let's thank Milan again for the talk.